Hello and welcome back, everybody, to this yet a new season of Infosys Chandrasekhar and Random Geometry Colloquium. Today, we're extremely glad to have Deeparaj from MIT, who will talk on SU2 representations of three-manifold groups. Over to you.
Thanks for the introduction and the invitation to speak. So I'll be talking about three-manifold groups for today. And here are our main spaces of interest. I'm going to be thinking about spaces of SU2 representations of my three-manifold group. And as some of the audience might be familiar with the character variety, I'm not going to be talking about the character variety. I'm going to be talking about the representation space itself. So I'm not modding out by conjugation. Here are some variants that I'll be thinking about. So throughout this talk, Y is going to be a closed oriented three-manifold. K is going to be a knot. In particular, K is connected. And the second variant is about, you look at the knot complement, you look at representations of it, and you add this traceless meridional holonomy condition. That's to make sure that, this is like a well-defined and smooth object. And another variant that will show up for a brief amount in the talk is this one where you ask for the meridional holonomy to be minus identity on the nose, right? Omega is oriented one submanifold. Yeah.
Sorry, what is mu?
Nu is the meridian.
Sorry?
Meridian of your knot. And yeah, omega for us will always be connected. So nu is also just the meridian of omega.
Okay, so basically this R hash of Y sub omega is basically the same thing as Y minus K with rho mu equal point.
Yes, but the point is that this is more of a topological condition and the middle one is more of an analytic condition. I will maybe stress that at the appropriate juncture, but for now, let's just stick to these definitions.
What does that mean?
I'll get to it when the time comes.
I mean, you're not allowing knots to isotopy.
No. It will turn out that this one, the last one depends only on omega up to its homology class, but the middle one depends on the isotopic class of K. So, yeah. Anyway, all right. So we'd like to understand these spaces. These spaces could be singular and, could just be very bad spaces in general. So we'll set our goals slightly on a simpler object, which is to try and understand homology of these spaces. But that's also not a great idea because these spaces might not be manifold. They won't have Poincare duality or anything of that sort. We want something more well behaved. So what we're going to try and talk about are these groups Y, I sharp, Y, K, and I sharp, Y sub omega. And all of these come from the respective representation spaces. And these are my so-called instanton groups. And I'll tell you what the construction is now. So here's a sketch of the construction. There is a so-called Chern-Simons functional on your space of connections on a space that comes from, so A sharp is space of connections on a manifold Y sharp that you build out of Y. I'm not getting into the details of how you form Y sharp from Y, but for now, let's just say, there's some space of connections on some other closed three manifold. And there's the Chern-Simons invariant. I won't give you a formula for it, but I'm going to tell you what it is up to a constant factor. And what I mean by that is, I'm going to tell you what its gradient is. So the gradient is negative Hodge star of the curvature form, right? So in particular, notice that it's invariant under the gauge group. So we can now just quotient out by the gauge group. This guy is a one form, yes. Three-dimensional Hodge star dual. So yeah.
But one proportion that gauge group, the value should be R by.
Yes, I was going to say that. The point is that this thing defines a non-trivial homology class in this space. So you can at best hope it to be R mod Z valued, not better than that. Okay. Now, the upshot of this is that the critical set. Yeah.
Usually, if you're putting candles, then there is a standard functional FA, which FA star.
Yes, but
You know what it's called?
it is the exact same. It's just I wanted to skip the gradient computation and instead define it using this. And yeah, yeah.
And it's independent of the co-manifold.
Yes. I mean,
Basically, A wedge A plus A wedge A wedge
with a 2/3 term and things of that sort. The point is I want to put the gradient on the pedestal because that's what we care about the most. And once you know what the gradient is, you can check whether it's a closed form and then use that to define this abstractly. And that's going to be good enough for our purposes.
And you're not restricted to flat direction.
No, I mean, that's my critical set, but I'm going to do more than that. Yes. So, yeah, as Mahan already sort of alluded to, the critical set is going to be flat connections and flat connections are in one-to-one correspondence with these, depending on what sorts of connections you pick. So for this model case, it's just going to be R sharp of Y, right? Now, this is an infinite dimensional manifold. Yeah.
Target is clear. That's something the character right here.
That's what the sharp is for. My manifold is not, my underlying three manifold is not Y. It's a three manifold I constructed out of Y. And that out of Y thing, I add like a connect some piece that kills the conjugation action.
Yeah, but what I'm saying is that even if you take instead of R sharp, you take the character variety.
Modeled by conjugation, yeah.
Also. Then this critical point set, is it really R sharp, or I mean, do you really get map broad?
So you get character variety of Y sharp, and the character variety of Y sharp is R sharp of Y. Yeah. Did somebody have a question at the back?
Okay. There's something going on there which might need to.
Okay. Okay. So, all right, you have the critical set of your Chern-Simons functional is this, and now if this were transverse and smooth and cut out nicely, you could try and just take homology, but instead what we're going to do is we're going to utilize the fact that it's the critical set of some functional and do Morse theory on that functional. Now, there's of course a lot of subtleties about trying to do Morse function in infinite dimensions rather than finite dimensions, and I will not elaborate on what those subtleties are or how you deal with them. Instead, I'll just say that from here, we get a chain complex with a differential, and the differential is by counting sort of Morse trajectories. The chain complex is freely generated by the critical points of once you make them, zero dimensional. And once you're done all of that, you've got this chain complex, you can take its homology, and that's what we'll define as, in this case, I sharp of Y. And in the other cases, we have very similar constructions. For like Y comma K, I'd have Y comma K sharp, and analogous constructions would apply, right? And this is the very brief sketch of this, but I'm sure this isn't very satisfying. So let me tell you some properties that you should keep in mind out of this construction.
Better put the front board down just to keep the stuff you just written.
Yeah, but I don't expect this to be very illuminating. So this was just to tell that, okay, this is something that you might have seen before. And if you've not seen it before, it's fine. I'll tell you some formal properties, which is what you should really concentrate on. Right? So properties. So unlike your usual homology groups, these are not going to be Z-graded. These are going to be Y sharp, Y comma K, etc. are all Z mod 4 graded. So there's, yeah. And so you can still talk about its Euler characteristic because it's, Z mod some 2n sort of grading. And then the Euler characteristic of I sharp of y is topologically determined. And in fact, if y is greater than 0 and the size h1 by y is
Purely determined by homology. This is
of the base Three-Manifold, yeah. Yep. So B1 is the first Betti number with rational coefficients. Yep. And
this is I sharp y or I sharp y k.
yes, that's not I sharp yk. That's just of the Three-Manifold. Yeah. In fact, you can even put an omega if you want. The result stays the same. And another case I want to talk about is the Euler characteristic of I sharp of S3. So your ambient manifold is just S3 and you have a knot in there. So for this result, it's important that K is connected. Okay.
So it's two.
This is always 2, yes. Think of it as twice the evaluation of the Alexander polynomial at 1.
Nice.
That's not true on the nose, but in this particular case, it is true. Yeah. Okay. Any questions about this very quick and dirty tour of instanton floer homology before I get moving? Okay. Right. So let me export now. Actually, yeah, okay, let me do this. Something on this and okay. So here's a folklore result. Call it folklore because I wasn't able to find a good reference for it. So if the Chern-Simons functional is transverse to 0, so in particular, this implies that R sharp y or whatever other variant is there is smooth.
Sharp y k or
Just the first bullet point over there, R sharp y.
imply CS is not.
The Chern-Simons functional, so the functional that I mentioned some time ago, but yeah. I mean, we'll never be checking the transversality assumption in all of these examples. I'm going to just tell you it holds or it doesn't hold. And yeah. So in this case, there is a spectral sequence from the homology R sharp y to I sharp of y. And this holds even for all the other variants. So
Essentially, because R sharp y is a critical set of CS, that's why it's.
Yep. So this is exactly the Morse-Bot spectral sequence if you have seen it before. And let me just write that down. Morse-Bot spectral sequence. A good reference for this for the finite dimensional case is Austin and Brahm from the 90s. But we're using sort of a souped up infinite dimensional version of it, which unfortunately I couldn't find a great reference for. But yeah, so this is to just put in context that I sharp really is sort of the best thing you could talk about as homology of R sharp, even when R sharp is singular and does other weird things.
Yeah, what kind of homology are you looking at?
This is just singular homology. Yeah, this is just your usual singular homology. So this is smooth, and because for some compactness reasons that are independent of this transversality.
Convergence H star.
This is your homology group, and this has a filtration which is by the connected components of this thing. Yeah, and that filtration gives you a spectral sequence. So really speaking, I think this is the E2 page. Oh, the filtration. Okay, yeah, that's based on the connected components, and I want to say the sort of relative index, but because it's Z mod 4 graded, that doesn't quite make sense. I mean, for the same reason that that's not Z graded, does not quite make sense to talk about it, but there's a little bit of work, extra work that you can do to make this story kosher. The differentials within the component is going to it abuts at a finite state. Yes, that is true. All of that comes from some compactness properties. So these are going to be closed compact manifolds. They might not. They will also be oriented, I believe. And this will abut at some finite range. Yes. So this is going to be, like the E0 page of. So this is the E2 page, I believe. And the E1 page is going to be, everything is going to be free and finitely generated Z modules, and so is the end result, and it abuts at a finite state.
By that you mean that every term converges at a absolute finite state. Not that there is a page in which the whole thing, not that there is a case that k equal to infinity. That's not it.
So, sorry?
Not that there is a case that k equal to infinity. You don't mean that. You mean every point converts.
I don't see why the latter does not imply the former.
So I'm just asking.
Yeah. I think the whole page itself, it's not just box wise or anything like that. Yes, for some k. Yes, I think that's.
One part in usual one part setup, C graded one part.
Yeah. Only if it's a finite type. If your ambient manifold is closed, I think it's still true. Yeah, if it was a proper Morse function on a non-compact space, then you're right. Each slot converges, but not the whole page. Yeah, but this is more akin to Morse-Bordner's theory on a closed manifold. Yeah. So yeah.
Secretly, I was doing some compactification of this kind of variety by some GIT or something like that.
I mean, it's compact as a core space, right?
Yeah, so for which means that you have to add on this GIT, and you have to make the GIT quotient.
Yeah. So okay. What I mean to say is this. So when you do the GIT quotient, right, you take only your stable points, and you need to then add your semi-stable points as extra, right? Over here, we don't care about semi-stability, polystability, stability, none of that. We just add everything we can as a coarse moduli space, so to speak. And once we have that, we deal with the singularities by perturbing the function instead of trying to figure out what the structure of the singularity is. So you're right. If you are thinking from a more algebra geometric perspective, you need to worry about what points are semi-stable, what points are stable, what points are polystable, and then carefully figure out how to glue these points, from one stratum to another, and figure out what you mean by homology of such a space. But we're going to avoid all of that by just thinking of trying to do infinite dimensional Morse theory for a function.
Yeah.
So.
If you understand details, you can add a perturbation.
Yeah. But the thing is, so in some sense, this is resolving your space, right? But I'm not telling you how we're doing the resolving. That's all taken care of by the setup, the way things are set up. And
part of the Y.
This is part of my Y hash. Indeed, I would call it Y sharp, but Y hash as well. Sure. But yeah, so I'm the ambient space A sharp mod G sharp. That's where all this resolution is happening, and it's happening through this function. And we don't try to pinpoint how that happens.
So it's reducible there.
No, reducible. The point of using Y sharp is to make sure there are no reducibles. Yeah. Right. Okay. Cool. Now, just based on this folklore result, we can have a bunch of examples. So let me go to examples. Right. So let's start off with the most trivial examples, because with all of this baggage, even that might seem daunting. So let's just take y equals S3. In this, R sharp is just a single point, right? Okay, so that's great. Your representation variety, I mean, your representation space is connected. So there is no, it collapses right on the second page, right? That's great. Upshot is that. So I've not told you anything about how the gradings work. All I'll tell you is that the gradings do work out, right? And in this case, because of the grading conventions, you get that it's Z concentrated in grading 0, right? And let's also do a pair. So that's S3 comma the unknown. Then in this case, you have so let me explain why this is. So you're looking, so once you take the complement of the unknown, what you've got is a solid torus, and it's the thing that generates its fundamental group is the meridian, and you put the constraint that the meridian has to be traceless. Now SU2 is homeomorphic to S3, the trace is, so the trace gives you a map to this interval. You have S3 homeomorphic to S2, and any point in the interior has pre-image S2, right? So that's why this representation space is S2. And again, by some grading conventions, this turns out to be Z in grading 0 and Z in grading 2, right? So far, nothing out of the ordinary, and these spectral sequences collapse because the transversality condition is, so first of all, there's a spectral sequence because the transversality conditions are met, and the spectral sequence collapses right on the second page because the representation spaces are connected, right? Okay. So now let's try doing a slightly more non-trivial example, right? Where here we're going to rely on results that have been non-trivial results that have been proven. So let's take Y to be the Poincare homology sphere. So people who are more comfortable with orbifolds will see it as or cipher fibered spaces. This is S2 with 3 singular points of order 2, 3, and 5. Right? You can also see this as +1 surgery on the right-handed trefoil. Are people okay with Dehn surgery of 3 manifolds along knots? I'll take that as a yes. And so this is another way of thinking about it. And over here, the representation variety or representation space is interesting. Here's what it is. So you have a point corresponding to the trivial representation. Disjoint union, there is an SO3, which is corresponding to the representation rho plus, which is just A phi embedding inside SU2, right? And there is another SO3, which is the same thing but composed by a reflection, right? Okay, so one would naively think that since the homology of manifolds, let's just work with rational coefficients for now. This is 5-dimensional because with rational coefficients, this looks like an S3, right? So that's 4, that's 1, that's 5. I'm not telling you anything about the grading. You can figure that out. But a result that is known is that this with rational coefficients is just Q at grading 0. And this result requires an attribution. So let me do that. This is due to Chris Caruto from 2015. So pretty recent, given that Floer theory was there in the 90s.
One second. So, why did you write SO3? Because you have rho plus and you have a SU2 orbit of SO3.
Yeah, and this is irreducible. So you take SU2 mod the stabilizer. The stabilizer is Z mod 2. Yeah, the center is always in the stabilizer. So your final orbit spaces should not have any center elements. Yeah. So yeah, that's why it's an SO3 and not an SU2. Is things okay? Right? Okay. So we already see that this is one instance where the spectral sequence does not collapse on the E2 page. And this is one of those cases where you can actually get your hands dirty and compute the spectral sequence and see exactly on which page it collapses. But I'm not going to do that. I'm going to instead move on to another example, which is going to be, I'm going to keep this here actually, and pull this down instead. Yeah. So let's look at the pair 3, T23, which is just the right-hand tetrafile. I'm using this notation in case anybody is familiar with torus knots and they recognize it. Then in this case also, so let me tell you what R sharp is. There's a point corresponding to an abelian case where you send the meridian to one thing and make everything else commute, which kills everything else as well. And there is another irreducible representation that survives. And this can be seen by the standard presentation of the peripheral group of T23, right? I'm not going to go about that computation, but what I will say now is that the spectral sequence does collapse. Yes, the middle bullet point. For this case, yeah. Yeah. And so this, yeah. Yes, and it's generated by the meridian. Oh, sorry, my bad. I confused my three-manifold case with the knot case. This is supposed to be an S2. It's just like the case of the unknot. Yeah, my bad. Yeah. So yeah, once I've done that, I know the meridian is going to be that, and then it has an S2 orbit because the stabilizer is U1. Yeah. Right.
When you have some trivial thing, then you have S2 and the other component.
That's when the knot is non-empty. If the knot were empty, so I'm talking about say R sharp of Y, then yeah, whenever it's abelian, then it's just going to be determined by the. Yes, indeed. Yep. And this is true even in the three-manifold case. Yeah. So in this case, the spectral sequence does collapse. And in fact, you get that I sharp S3, T23 is going to be homology of S2. And there's a grading shift for the homology of SO3. So the grading shift is going to be 1. So that's that. But I want to point out that the spectral sequence collapses for, not great reasons, in the sense that if you put in a local coefficient system, the spectral sequence will then fail to collapse. And there is an example of a local coefficient system that's known, for which you get something more interesting than just homology of this, homology of that, with some twisting of the local coefficient system. So what I mean by that is, these differentials, they count some sort of Morse trajectories, right? What I want to say is that these Morse trajectories are non-empty, but they cancel out. They're going to get paired up, and they come with opposite signs as well, so they cancel out, and that's why you get this. But this is not for the same reason what happens in the case of the unknot or S3. They're genuinely just the low dimensional moduli spaces are genuinely empty. Okay, right. This is a good spot for me to stop for questions about the gadget that I'm using. All right, if there are no questions, I've told you about the gadget I'm using. Now I need to tell you how I'm. Yeah.
Have or not. For instance,
This is.
we're going to have S2. And if there is an irreducible representation, you have S43.
Yes, but they might not be isolated always. If you take a complicated enough knot, the S2 is going to remain isolated from the SO3s, but the different SO3s could sort of join together and in some complicated way. There is no reason to expect them to be isolated.
So that's basically provided to have more than one event.
Yeah. If you have more than one, you have no reason to believe that they're isolated. But
And so the other thing is, I think, this compactness is actually bothering me a little bit. In the sense that, for example, you have this very complicated three-manifold group of complement.
So let's just look at the definition over there. I'll resolve compactness from there instead of using some other high-powered machinery.
I was actually looking at the various. So
this is, your three-manifold group is always going to be finitely presented, right?
It's basically going to be decided by the generating cell. So
Yes, exactly.
That's okay. What I'm saying is that if you look at the irreducible components, why can't there be wide behavior? Differently, when components converge into something.
Oh, that can happen. I never said that the things are. There could be. You could have something like. What should I talk about? Let's talk about S1 times S2. All right. That one is going to be an SU2, right? So that has not fallen into this dichotomy of S2, SO3, or point, or any of these things. So you have the right to question, what is that really? And what it is it fibers over the interval. You take the trace map. So for each trace, that determines the map up to conjugation. And that's going to be an S2, the fiber over it. And you have this S2 times interval, and at the end you collapse it. Sorry, what?
So you have SO3 cross interval or S2 cross interval?
I said S2. Yeah, because they're all abelian. They all have stabilizer U1. So those are your S2s, and all of these S2s are sort of infinitely close to each other. They're not isolated like how you expect them to be. And in fact, the compactness issue might have been, what if you go towards n plus or minus 1, right?
No, this is still a fixed smooth object, right?
This is smooth, but this is not this is Morse-Bot, yes, but it's Morse-Bot in a more complicated fashion than the ones I've talked about. Okay.
What I worried about that is suppose you have serials of homomorphisms.
Mhm.
515.
Yeah.
Representation variety in general is some compact weird object.
Yes.
Right.
Yes.
So, and it's got all this. I mean, in order to do that compactification, we have to throw in various things at infinity. So
All of that is done for us directly because it's like you said, it's an SU2 times some number of generators. We are not saying anything about the topology. So while I'm saying that, this is really as a course object.
So essentially what you're saying is you look at each of the, so that's basically where you use the finite presentability rather than finite generation.
Yeah.
Each of those presentations, they give rise to some quotient.
Yeah.
Some codimensional thing, and then
you don't know how they intersect. They could intersect very badly. Whatever happens, we don't care.
Right.
It's some real algebraic variety.
Real.
Yeah. It's going to be very singular. We're not going to deal with it directly for that reason. Yeah. All right. Okay. So I told you about the gadget. Now let me tell you about what use I have for it. And yeah, started from this. So from the abstract, the main question that I'm trying to answer is, how do we find representations? And all I've told you so far is, well, if you have found all of them already, I'm telling you some gadget that you can compute, but that's not helpful. What is helpful is doing the other way around. So the hope is that this gadget is flexible enough that you can compute it independently of computing the representation space, and then say something like, okay, the representation space had to have had an element of this sort and so forth. So the first result, or the result of that nature that's relevant to us, is this is due to Baldwin and Sobek from 2021. So if for all rho the image subgroup is abelian, and you need another homological condition on Y. So I'll just, instead of elaborating on what the condition is, I'll just tell you what the upshot of it is. Then that spectral sequence collapses, the Mossbot spectral sequence I mentioned. And in fact, what this means is that, does this always keep slowly moving? No, okay. Then the evil grading, so 0 and 2, this is a free Z module. So I'm using the abelian condition to say that the stabilizer is either U1 or SU2. So all their orbits are going to look like points or S2s, all of which have free homology, right? So you have that, and the way the grading works, we're going to have this as well, right? So what this means is, the way to try and find irreducible representations or representations with non-abelian image is going to be, we're going to try and show that one way or the other, I sharp has either the odd grading bit is not equal to 0, or that this bit has torsion as a Z module. Then we know that and we'll also check that the homological condition is satisfied, whatever that is. Then that means that there had to be an irreducible representation. And this is going to be our strategy. Okay. Now, for the strategy to work, I need to tell you how to compute this error when the spectral sequence does not collapse. So far, all I've told you is, here's a case where it does not collapse, and I've not told you how it's done. Or the other cases are all where it collapses, and sometimes for non-trivial reasons. But let me try saying a bit about how one would try and start to compute these instanton groups, right? So what should I do on this board? Okay, let me just keep the pattern. We can set this out. So what we want is, how do you compute? So let's go back to singular homology. How do we compute things over there? What we typically do is we know it for some very simple cases like spheres, disks, and then you just here with Mayer-Wettorus, right? You take a CWT composition, which is basically you glue in cells to one another, and once you have such a decomposition, you use Mayer-Wettorus to try and compute the homology. I'm not saying it's always easy, but that's how we typically go about it. So we'll try to do something similar over here. And the name of the gadget in this trade is called exact triangles. You should think of these as long exact sequences, but we can't quite talk about long exact sequences because the grading is not Z graded. So it does not die at some stage. It just keeps going on, and at some point it wraps around. So I'm going to instead draw them as triangles with, there's going to be some grading shift at some places, but you should just think of it as at every spot, the kernel of the arrow that goes out of it is equal to the image of the arrow that gets in, right? Okay. So the first result in this direction is due to Andreas Floer himself, and this is in 89, I believe. I don't think it ever made it to publication. It was as a preprint, but anyway. Let K be a knot with some framing. So by framing, all I mean is the information about how you glue in a tubular neighborhood of it, essentially. Okay. Then you have the following exact triangle. I mean, when he said this result was not exactly in this form, but this can be seen as an immediate consequence of his original result. N is any integer. Sorry. Yeah. Yeah. So omega n is going to be one submanifold that depends on n, but it has a fairly explicit description. It's essentially going to be the dual knot inside this n surgery, right?
Why is the n surgery?
Yn is the n surgery on k, yn plus 1 is the n plus 1 surgery. Yes, the typical notation is, so let me call this ym, is ym of k to denote that you're surgering along k. I'm just omitting that knot, right? So, yeah.
But what is omega n exactly?
It's so you glue in a solid torus, right? It's the center of that torus.
Okay.
Yeah, that's what I meant by the dual knot. Yeah. So, all right, this is a result. There are two main drawbacks. First, you don't already have a table of computations to build off of for three manifolds. Like the example that I just erased, that is computed using other methods. Any knot, any three manifold, yes. But it has to be a knot, so one connected component. Yeah.
Integer.
Yes, that is a very annoying. Yeah. Yep. Unfortunately, we haven't, so far at least, there haven't been any real upgrades in that regard. But you can do slightly better. You can, I said any framing. You can rig the framing to get 1 over n and 1 over n plus 1 and things of that sort. But you're right, you can't just do p over q. Yeah, you can't do the general thing, but you can get a little beyond just integer. You can do 1 over integer. But yeah, you're right, not very impressive. Sure. But we don't have a catalog or a table of three manifolds and their instanton groups to start this computation to begin with. So that's one drawback. Another drawback is even though these maps are sort of geometrically defined, you can't compute them. So what's the point? You will know maybe two of the groups, you can't compute the map in between, you're still back where you started. Okay. So to remedy that, the point is we shift some of the, the power to the not instanton group. And the reason for this is not instanton groups are computable in terms of more combinatorial defined invariants. I'm not going to get into that rabbit hole entirely, but this is just to say that not homology group, yes, we can maybe compute it. Three-manifold group, probably not. Right? Now, result that I've proven in this direction is that you have, using the same surgery notation, instead of n to n plus 1, I've got n to n plus 2. I got rid of the omega n and I've replaced y with y comma k now. Any not any three manifold, yes.
Yeah. This is basically some packaging of a long exact sequence, right?
Yes, yes.
So I mean, and this is an n plus 2 surgery on that not k.
Yes.
Yeah, I see.
So I'm basically put two of them together, but I've not done it in a very simple way. I've done something more complicated and geometric, so to speak. And yeah, so that's why you don't see just two copies of I sharp of y or some other object of that sort. You see y comma k instead. And the point is, this is more computable. And going back to that and trying to contradict the conclusion of that theorem, the point is that not only can you compute this, this also often has two torsion. If it has enough two torsion, then at least one of these also had to have had some two torsion. Exactly. That's going to be our mechanism of proof. So, I mean, that's still easier said than done. These maps are geometric, but you can still not compute them. So what you want to do is put all of the heavy lifting on this group. And there are examples where you can do this, but to get a larger class, like a whole infinite family of examples, you need to do a little bit more work. And
this is the traceless.
Yeah, this is the traceless one. So that's the middle bullet point. Yeah. So yeah, this is what we'll try to do. And now I need to, how much time do I have left? 10 minutes, right? Okay. So, all right, I'll cut to the chase then instead of trying to beat around the bush. So, what did we have here? On the right-handed refer. I can get rid of that. So unfortunately, due to lack of time, I won't get to elaborate too much on the next result, but I can tell you what it is and also how it closes on the original strategy. So the result is as follows. This is, oh, I forgot to mention this. I should have mentioned it. Yeah, anyway. This is in collaboration with Zhenkun Li and Fan Ye. It's work in progress. But the result is that if K in S3 is fibered and you take your usual ciphered framing of your knot inside your three sphere, then we have been able to show that of S3 plus one surgery along K with, let me just call it K hat to mean the K hat, it's basically the image of K inside this three manifold. This has, yeah.
K hat is the core, right?
Yeah, K hat is the core, but I just don't want to call it K, that's all. And K bar is used for mirrors of, yeah. Has two torsion. This is not apparent from any part of the story that I've told you so far, even what a strategy would be, but I don't have enough time to elaborate too much on it. So I'm just going to state this result.
So just one thing.
Yeah.
So for fiber knots, these are detected by these twisted Alexander polynomials, right? This Beadle, we know, see, we did some stuff about to take it back.
Oh, I didn't know all fiber knots can be detected that way, but yeah, I can believe that there is a result of that sort. Yeah. Okay, I've not seen the reference myself, but yeah.
Yeah, I was just wondering whether that feeds into this in some
In a very indirect ways, not exactly that detection result, but there is a detection result by Yi, which says that knot floor homology detects fibered knots. And the way it detects it is there's this top non-vanishing grading. If that's rank 1, then it is fibered. And the top non-vanishing thing is going to be the genus of the knot. And so, like, it's well defined and everything. And so you just look at that, see if it's one-dimensional or not. If it's one-dimensional, it's fibered. And that part of the story, the story of Yinis, that does feed into this in a very roundabout way, but it does have an impact. Yeah. So, or at least rather than saying it feeds into it, let me just say they're related. Yeah. Okay. So this has two torsion. Now you pick your framing very cleverly, which is you set nu dash equals nu plus lambda, where nu comma lambda is your standard ciphered framing. And I mean, this is meant for the experts, but I will say what the output of, what the upshot of this is. And lambda prime equals lambda. So what this means is, if you look at
essentially what you're saying is it means the intersection of the cipher surface with the boundary.
nu is the meridian, lambda is the intersection of the ciphered surface with the, yeah. Yes, nu is the meridian, just like in there. Yeah. So this is now going to be nu. This is going to be nu plus 2 lambda. So what that means is once I use this thing, let me keep that code over there. Let me instead. Yeah, you know what? There's no winning this. Yes. I thought better about this, but yeah. Right. So the result that's just behind this board. Great. So the result, unfortunately, which is behind the board, tells you that you have I sharp of S3, that's the -1 surgery. You just cap off your meridian, so you get back S3. You have +1 surgery, that's 1/2. And you have this comma k hat. So this has two torsion, but that still doesn't mean too much, because here's an exact triangle where this is multiplication by 2. So this is not good enough, but with a little more work, we are able to show that this particular case cannot occur. We won't get into that story all, but I will say that it's not that much work. And again, this is joined with Zhenkun Li and Fan Ye. And we just have the corollary. It's 3 half K admits an irreducible representation. And for example, this applies to the figure 8 knot. So, and you also know that +half is not an exceptional surgery slope for this hyperbolic knot. So you have some hyperbolic three-manifolds that show up in this context as well. And I think I'll end here. This is what I wanted to say. Thanks.
Now we can open questions for the bunch.
So does this thing apply for are there cluster of surgeries or not, which gives us homology sphere?
You mean integer homology spheres? All of them do.
Right? Obviously.
That's just for sort of homological reasons. As far as you're computing homology with integer coefficients, you can treat it like the not. And for that, yeah. Yeah, all of these are integer homology spheres. That was one of our original interests to begin with. Yeah.
Yeah, so where is the fiberness of this? How it
Use it here. We don't need it in this part. In the proof. Right. So fiberedness first tells you that this somehow this extremal graded piece in some flavor of not instanton homology is going to be one dimensional. So I told you about this one Z mod 4 grading, right? There are other flavors of instanton floer homology that have a bigrading. One of that is this Z mod 4 grading, and the other one is an integer grading. And you're supposed to think of this as, I mean, the name is very suggestive. It's called an Alexander grading. And this is, as you might be led to believe, it's related to the Alexander polynomial of a knot. But
what is the grade?
how, I can't define it, and I don't know of a good geometric description of it because,
I mean,
yeah.
Does it have anything to do with the Alexander polynomial?
Yeah, if you take an Euler characteristic with respect to the Z mod 4 grading, but take sort of a par series sort of thing with respect to this Alexander grading, you get the Alexander polynomial. So it sort of categorifies the Alexander polynomial, this Alexander grading. So you're supposed to think of this as you might have heard of Quano homology, how it comes with a bigraded thing, and you can take its graded Euler characteristic. So along one graded direction you add pars of Q, along the other one you take an actual Euler characteristic that recovers the Jones polynomial, right? So this is the version of that story for the Alexander polynomial. That's the grading that.
What is extremal?
Extremal as in the largest non-vanishing one. The largest non-vanishing one is going to be one dimensional because of the fiberedness condition, and that, for example, tells you maps from it are either zero or injective. That plays an important role, for example. Yeah, I would be happy to say more. It's just I didn't have the time during the talk, so yeah.
By the way, what is I thought this was C mod 8 grade, but maybe I'm missing that.
Yeah, you're missing the sharp. Yeah.
That is C mod 8.
Yeah, it's if you had an integer homology sphere, then it is Z mod 8 graded indeed, but I've not told you what the star apparatus is. And yeah.
So let's see. The Casimir invariant is supposed to be a lifting of the Rockley to C mod 8 or C mod 16.
No, the Rockley invariant is Z mod 2 Z mod 2, and the Casimir invariant is an integer lift of it. Yes. And no, Z mod 2, because Z mod 8, you already know your thing is going to be multiple of 8, and then you check whether it's a multiple of 16 or not.
Okay. Yeah. That's right. Smooth implies.
Yeah. Smooth and spin implies 16. Yes. Yeah.
The 8 also comes from there. Because I think due to the 8.
No, it does not. In the index formula, there is another term that contributes to the 8 thing. It happens to be a coincidence that your theorem about unimodular lattices says they're divisible by 8, and there's another factor of 8 that happens to show up there, but I don't think there's any real conceptual relationship. Yeah.
Yes, sir. Those questions for the
Should I have done this one?
Thanks.